Imagine standing on Earth, looking up at the night sky, and realizing that each twinkling star represents a world that might never be reached. Humanity has always dreamed of travelling to the stars, of exploring distant worlds and touching the edge of the universe. But what if I told you that the very laws of physics, the rules that govern space, time, and energy, make interstellar travel far more impossible than we ever imagined? Tonight, we are going to journey beyond the rocket ships and science fiction into the cold, unforgiving reality of the cosmos. We will uncover the invisible barriers that prevent us from reaching even the nearest star, the extreme forces and dangers that lurk in the void, and the technological and energetic hurdles that challenge our wildest dreams. By the end of this exploration, you will see why the universe is both our greatest inspiration and our most uncompromising teacher, showing us the limits of what we can achieve and the vastness of what we have yet to understand. Buckle up, because this is a journey where imagination meets reality, and the impossible becomes a story of wonder, caution, and discovery. When we think about travelling to other stars, it's easy to underestimate the sheer scale of the universe. The closest star to Earth, Proxima Centauri, is about 4.24 light-years away. That means light itself, moving at the fastest speed possible in the universe, takes over 4 years to reach it. Now imagine a spacecraft, even one travelling thousands of times faster than current rockets, attempting the same journey. The distances are so vast that they dwarf anything we experience on Earth. For context, our fastest spacecraft, like the Parker Solar Probe, moves at tens of kilometers per second, but at that speed it would take over 17,000 years to reach Proxima Centauri. The emptiness between stars is not just a void, it is an almost unimaginable expanse of cold, dark space where no resources exist. Unlike a journey across a continent or even a solar system, there are no gas stations, repair shops, or safe harbours. Every bit of fuel, every piece of life support, and every system must be carried on board from the start. The vast distances also make communication nearly impossible in real time. Messages would take years to arrive, even to the nearest stars. Our understanding of distance in everyday life simply fails when applied to interstellar space, because numbers like 4 light-years hide the true enormity of the challenge. Traversing even the smallest interstellar distances requires rethinking time, energy, and human endurance in ways that our current technology and imagination struggle to fully grasp. One of the most fundamental obstacles to interstellar travel lies in the rules set by Einstein's theory of relativity. According to this theory, nothing that has mass can reach or exceed the speed of light. As a spacecraft accelerates closer to light speed, its relativistic mass effectively increases, requiring exponentially more energy to continue accelerating. At a certain point, the energy required becomes infinite, making it physically impossible to reach or surpass the light barrier. This limitation is not just theoretical, it is a fundamental law of the universe that governs everything from subatomic particles to massive galaxies. Even if humanity could develop propulsion systems far beyond anything we have today, we would still be constrained by this universal speed limit. Travelling at a significant fraction of light speed introduces strange and counterintuitive effects, such as time dilation, where time for the travellers slows relative to those left on Earth. While this might allow a crew to experience a shorter journey, it does not reduce the enormous energy requirements or the dangers of travelling through the interstellar medium at near-light speeds. Collisions with even tiny particles would release catastrophic energy, turning ordinary dust grains into deadly projectiles. The relativity-imposed speed limit makes clear that there is no shortcut through space. Accelerating to near-light speeds is not simply a matter of building a faster engine, but a fundamental wall imposed by the universe itself, shaping the physics of any attempt to reach other stars. One of the greatest barriers to interstellar travel is the staggering amount of energy required to move even a relatively small spacecraft across the immense distances between stars. Current propulsion methods, such as chemical rockets, are woefully inadequate for interstellar journeys because the energy they produce is tiny compared to what would be needed to reach even a fraction of light speed. For perspective, accelerating a spacecraft to just 10% of the speed of light would require more energy than humanity currently produces in an entire year. The relationship between mass, velocity, and energy grows exponentially as speeds increase, meaning that doubling the speed of a spacecraft requires far more than double the energy. Theoretical solutions like nuclear fusion, antimatter engines, or matter-antimatter annihilation promise higher energy yields, but they face enormous technical and safety challenges, and none are close to practical implementation. Carrying enough fuel for a long interstellar journey presents a paradox. The more fuel you carry, the heavier the spacecraft becomes, which in turn increases the energy required to accelerate it. Even solar sails or light-based propulsion, which do not carry onboard fuel, would require decades or centuries of continuous acceleration and precise targeting. The astronomical energy demands are compounded by the need to sustain life and systems aboard the spacecraft over potentially thousands of years, adding another layer of complexity. In short, the universe imposes a hard limit through energy requirements, turning interstellar travel from a matter of engineering into a question of physics and cosmic scale that humanity is currently nowhere near solving. Time behaves in strange ways when a spacecraft approaches the speed of light, a phenomenon known as time dilation, predicted by Einstein's theory of relativity. For travelers moving at relativistic speeds, time passes more slowly compared to observers remaining on Earth. This means that astronauts could experience months or years on a ship, while decades or centuries pass outside. While this might seem like a benefit for long journeys, it creates profound challenges for interstellar travel. So, for one, any mission to even the nearest star systems would still span centuries from the perspective of people on Earth, making communication and coordination across generations nearly impossible. Families, societies, and civilizations would change, leaving travelers isolated in a future world they cannot relate to. The longer the journey, the more life support systems, food, water, and mental health resources would need to be maintained without resupply, placing enormous engineering and logistical demands on the spacecraft. Additionally, extreme time dilation only occurs at speeds very close to light speed, which, as discussed earlier, requires near infinite energy and carries extreme risks from cosmic radiation and interstellar debris. The interplay between time dilation, human biology, and technology illustrates that interstellar travel is not merely a technical problem, but also a temporal one. Humanity cannot simply jump to another star without confronting the reality that our lifespans, even extended with relativistic effects, are minuscule compared to the timescales required for meaningful interstellar exploration. Travelling through interstellar space at near-light speeds introduces hazards that are almost impossible to mitigate with current technology. At such velocities, even the tiniest particles like cosmic dust or micrometeoroids become deadly projectiles. A particle smaller than a grain of sand could hit a spacecraft with the force of a high-powered bullet, potentially destroying vital systems or puncturing protective hulls. Cosmic radiation, normally dangerous over long durations, becomes far more intense at relativistic speeds. High-energy particles and gamma rays can penetrate shielding and damage both electronics and human tissue, increasing the risk of radiation sickness, cancer, or system failures. Unlike in Earth orbit, there are no magnetic fields or atmosphere to provide protection, leaving spacecraft and astronauts fully exposed. Collisions with interstellar gas, though sparse, would still generate intense heat and shock waves at extreme velocities, adding another layer of danger. Engineers might try to develop thick shielding, but additional mass increases energy requirements exponentially, creating a paradox between protection and propulsion efficiency. Even navigation becomes treacherous, as the slightest miscalculation at near-light speeds could send a spacecraft far off course with no opportunity for correction. At these speeds, the universe becomes a high-risk obstacle course where survival depends on precision, durability, and technology far beyond what humanity currently possesses. The combination of microscopic hazards, intense radiation, and extreme velocities makes clear that traveling safely through interstellar space is not simply an engineering challenge, but a fundamental obstacle rooted in the physics of high-speed motion. One of the most critical obstacles to interstellar travel is the fundamental limitation of our propulsion technology. Current rockets rely on chemical fuel, which produces thrust far too weak to reach even a small fraction of light speed, and scaling them up introduces enormous mass and engineering challenges. Advanced concepts like nuclear thermal or nuclear pulse propulsion offer higher efficiency and thrust, but even these remain orders of magnitude away from what would be required to reach other star systems in a human lifetime. Theoretical ideas such as antimatter engines, fusion drives, or light sails show promise on paper, but they face nearly insurmountable technical and safety hurdles. Antimatter, for example, releases tremendous energy when it reacts with matter, but storing even micrograms safely is a challenge humanity has not overcome. Fusion drives require sustaining a reaction that has eluded practical power generation on Earth for decades, and light sails demand perfect alignment with powerful lasers over unimaginable distances. Other speculative ideas, such as warp drives or manipulating space-time, currently violate known physics or require exotic matter that may not even exist. Beyond the technical difficulties, scaling up these propulsion systems to carry life support, shielding, and supplies for humans multiplies the engineering demands exponentially. Even if we could build a theoretically perfect engine, the universe imposes constraints through mass, energy, and the laws of motion, meaning that propulsion technology alone cannot overcome the fundamental barriers to interstellar travel. The dream of reaching the stars is constrained not by imagination, but by the cold, unyielding laws of physics that govern how objects can move through space. In exploring the physics that makes interstellar travel impossible, we have seen how the universe sets limits far beyond human imagination. From the unimaginable distances between stars to the speed limits imposed by relativity, from the astronomical energy requirements to the hazards of travelling at extreme velocities, and from the challenges of time dilation to the current limits of propulsion technology. Every aspect of interstellar travel reminds us of our fragile position in the cosmos. These constraints are not merely obstacles, they are lessons in humility, pushing us to understand the laws of nature more deeply and inspiring us to innovate within the boundaries of reality. While reaching other stars may remain out of our grasp for now, the pursuit of this dream fuels science, technology, and our imagination, showing that the journey of understanding is just as important as the journey through space. Good luck to everyone who dares to think beyond the stars and question what is possible. And thank you for joining me on this journey through the fascinating, unyielding physics of the universe. Keep your curiosity alive, because even when the cosmos says impossible, it is the questions we ask that define the boundaries of human knowledge.